Assalamu alaikum, brothers and sisters. Welcome to the journey of quest where we quench your thirst of knowledge. Have you ever wondered how fluids move and interact with their surroundings? Welcome to the fascinating world of fluids, a realm where liquids and gases hold sway. These two categories of matter might seem distinct, but they share a common trait that defines them as fluids. They both flow, yielding to the slightest pressure or gravitational pull. Let's delve into the heart of what makes a fluid, well, fluid. Picture a river swiftly coursing through a valley, or imagine a gust of wind gently rustling the leaves. These are examples of liquids and gases in motion, each demonstrating the fluidity that characterizes this group of substances. Now let's touch on some of the unique properties of fluids that make them so intriguing. First off, we have viscosity, a term that essentially refers to a fluid's resistance to flow. Think of honey slowly drizzling off a spoon. That's high viscosity. On the other hand, water cascading over a waterfall is an example of a low viscosity fluid. Next, we have compressibility, another distinguishing characteristic of fluids. This property determines how much a fluid can be compacted or squeezed. Gases, like the air around us, are highly compressible. That's why we can inflate a balloon by blowing into it. Liquids, however, are almost incompressible, which is why water doesn't shrink in volume when you put a lid on a bottle. These properties, viscosity and compressibility, greatly influence how fluids move and interact with their surroundings. They dictate the flow of rivers, the surge of tides, the gust of winds, and even the circulation of blood in our bodies. So whether it's the steam from your morning cup of coffee, the oil in your car's engine, or the air you're breathing right now, fluids are omnipresent, shaping our world in ways both subtle and profound. There you have it, a basic understanding of what fluids are and how their unique properties influence their behavior. Now that we understand fluids, how do they interact with themselves and their surroundings to reach a state of balance, or what we call equilibrium? Let's start by understanding equilibrium in the context of fluids. Picture a teeter-totter on a playground. When both sides are equally weighted, it's in a state of balance or equilibrium. Similarly, fluids reach a state of equilibrium when all the forces acting upon them are balanced. But what influences this equilibrium? Three major factors come into play: temperature, pressure, and concentration. Picture this. You're brewing a cup of tea. The higher the temperature of the water, the more quickly and thoroughly the tea leaves will infuse, changing the system's equilibrium. This is because an increase in temperature typically increases the rate of reaction, pushing the system towards equilibrium more quickly. Next, let's consider pressure. Imagine a soda bottle. When you open it, the pressure inside decreases, causing the carbon dioxide to escape in the form of bubbles. This is another example of a system changing its equilibrium state in response to changes in pressure. Lastly, concentration plays a critical role. Think about adding sugar to your tea. The more sugar you add, the sweeter it becomes. The sugar dissolves until it reaches a point where the concentration of sugar in the tea is equal to the concentration of sugar in the undissolved particles. This is the point of equilibrium. These factors, temperature, pressure, and concentration, continually interact with each other in a fluid system, influencing and adjusting the state of equilibrium. They can shift the balance, pushing the system towards or away from equilibrium until a new balance is found. But remember, equilibrium doesn't mean static. It's a dynamic process, a constant dance of adaptation and adjustment as the system responds to internal and external changes. Remember, equilibrium is all about balance. It's the state where all forces and influences are equal and opposite, leading to a state of rest or uniform motion. So we've talked about fluids and equilibrium, but what happens when we introduce a solute into the mix? Well, this is where distribution coefficients come into play. Now you may be wondering, what are distribution coefficients? In simplest terms, they're a measure of the relative concentrations of a solute in two immiscible phases. Think of it as a party where guests prefer one room over another. The distribution coefficient would tell us how much more the guests prefer one room to the other. Now let's put this into context. Imagine you've got a system with water and oil, and you introduce a solute. The distribution coefficient would tell you how much of that solute would prefer to be in the water versus the oil. If the solute is more soluble in water, the distribution coefficient would be higher for the water phase. And if the solute prefers oil, the coefficient would be higher for the oil phase. But why does this matter? Well, it gives us a predictive tool. We can use distribution coefficients to predict how solutes will behave in a system. For instance, if we know the distribution coefficient of a pollutant in an oil-water system, we can predict how much of that pollutant will end up in the water supply and how much will stay in the oil. But it's not just about predicting where solutes will go. Distribution coefficients also have a big impact on equilibrium. When solutes prefer one phase over another, they can tip the balance and shift the equilibrium of the system. For example, if a solute strongly prefers water over oil, it can cause the equilibrium to shift towards the water phase. In essence, distribution coefficients give us a mathematical representation of how solutes preferentially distribute themselves between two phases. It's a subtle art, but a crucial one, allowing us to predict the behavior of solutes and their impact on the equilibrium of systems. Okay, we've covered a lot of ground, but how do all these concepts connect in the real world? In the intricate dance of geochemistry, the concepts of fluids, equilibrium, and distribution coefficients come together to choreograph real-world processes. Let's take a detour and explore a few examples, shall we? Imagine the process of oil extraction. The oil reservoirs deep beneath the Earth's surface are essentially a complex fluid system. Here, the equilibrium between the oil, gas, and water phases plays a crucial role. The distribution coefficients, on the other hand, help us understand how different components, such as hydrocarbons, distribute between these phases. In essence, understanding these factors can help optimize extraction methods and maximize yield. Now let's shift gears to carbon sequestration. This process aims to capture and store atmospheric carbon dioxide to mitigate global warming. Here, fluids come into play as captured CO2 is often stored in deep geological formations. The equilibrium between CO2 and other compounds and the distribution of CO2 in various phases are key to ensuring its successful and safe storage. Lastly, consider water filtration systems. These systems rely heavily on the principles of equilibrium and distribution coefficients. As water flows through the filtration medium, contaminants adhere to the medium's surface due to their distribution coefficients. The system reaches equilibrium when the rate of adhesion equals the rate of release of these contaminants. Hence, understanding these principles can lead to the development of more efficient water purification technologies. So, there you have it. From extracting valuable resources, combating climate change, to ensuring our drinking water is safe, the concepts of fluids, equilibrium, and distribution coefficients are at work. They are not mere theoretical constructs, but driving forces behind many natural and industrial processes. As you can see, understanding these concepts is not just about theory. They have real-world applications that impact our daily lives. Let's take a moment to recap what we've learned. We embarked on an exploration of the captivating world of fluids, understanding their unique properties and the essential role they play in geochemistry. We then delved into the balancing act of equilibrium, a concept that helps us comprehend how substances interact with each other in a system and how they eventually find a state of balance. The subtle art of distribution coefficients was our next stop. We learned how they help us understand the partitioning of elements between different phases, providing valuable insights into geochemical transformations. It's important to remember that these concepts are not just theoretical constructs, but are the very tools that scientists use to unravel the mysteries of our planet. And with that, we've reached the end of our journey. Remember, the world of geochemistry is vast and complex, but also incredibly fascinating. Keep exploring, keep learning, and who knows what discoveries you might make. Thanks for watching us share our videos, subscribe our YouTube channel, and press the bell icon and stay curious for new uploads.